okay. So this university was appointed. This university received a double first-class, world-class disciplines and construction university in I think it was in 2017. So in principle, every year we can get some budget from the government. Because of this university was famous in texture, it was ranked as A+ in China. So, and also this university has the very strong background in engineering, chemistry, and material science that they are ranked as the world top 1% by ESI. And these are some pictures of this university. It seems that it's very good, and especially for this is the sports center. And now this is the place I'm working. I'm working in the state-K laboratory of separation membranes and membrane process. This state-K laboratory is very unique state-K laboratory. It has 4 platforms of hollow fiber membranes, membrane process, and engineering. This state-K laboratory is, I think it was, they made the first Chinese hollow fiber membranes for water treatment in 1974. And this state-K laboratory is a credit for membrane engineer and scientists. It participated in the 14 domestic membrane standard and also with 8 national awards of China. And one of the membranes that called one of the membrane companies called Mortec Membrane Company. It was a stock share. And also this state-K laboratory, they have the overseas expert plans called Overseas Expert Introduction Center for Display Innovation called 101 Center. And this center, they also welcomes the scientists for membranes from abroad, that both domestic and abroad, that can come here for the idea exchange and also support for the mutual collaboration findings. And this center has the largest membrane research teams in the world, I think. And it has 14 groups and almost 100 professors, especially on membranes. It has 500 postdocs and PhD and masters, over 7,000 square meters, experiment places and apertures and instrument over 300 million US$. So it's very big, and we are very open for collaborations. And then go to my group. My group focuses on the gas separation membranes. In principle, I'm working on 5 aspects. The first is the gas separation instruments. First, if you want to study a field that to get a very good information about the materials, you have to get the instrument to characterize it. Another aspect is about O2 separation and also low temperature CO2 capture. And I also work on some bottom-up structure property relationship for gas separation membranes and also hollow fiber membranes. And today, for the time issue, I will focus on the gas separation instrument and O2 separation, as well as low temperature CO2 captures. And this is the first part of work, the gas separation instrument. Here is the gas separation instrument for pure gas testing instrument. I made this or constant volume variable pressure instrument. They based on the constant volume variable pressure method. And this instrument is very small and integrated. We can test the flat sheet membrane, hollow fiber membrane, and modules. Especially, we can test one hollow fiber, and also we can test the modules. And we can test the low pressure and high pressure based on, because I made some changes of this instrument. Recently, we can test the water permeability and also some vapor permeability of this using this instrument. And because the gas separation, the permeability of the membranes for flat sheet and hollow fiber membranes, they based on the fixed law, and we can get reach the steady state based on the downstream volume and also the upstream pressure, and also the steady state flow rate. We can get the permeability of the membranes, and also based on the time lag, we can get the diffusion coefficient, and also we can illustrate the solubility coefficient of the membranes. We can get a deeper insight into the properties of the membranes. And this is another mixed gas testing instrument. This is their setups. For this, we can do the same thing for the flat sheet and the hollow fiber and the modules. And also we can do the high temperature and low temperature, high pressure, low pressure testing. We use the pressure transducer to get the mixed gas permeability, and we use the GC to test the component ratio of those different gases. As a result, then we can get the mixed gas permeability for each gases in this case. And recently we made another instrument especially for CO2N2, because the CO2N2 either from the flue gas or from other conditions, they are dry state. So I made this constant volume variable pressure dry and wet CO2 nitrogen separation testing. By controlling the wet and the dry gas, then we can get the upstream. We can send this gas to the upstream, and then we can use the transducer to check the accumulated gas in the downstream, and also we can use the GC to get the component of each gases. In this case, you can get the permeability of the membrane for CO2 and the nitrogen at dry state, and the mixed gas of CO2 nitrogen at dry state, and also the white CO2 and nitrogen at pure gas, and also the white CO2 nitrogen at humidity states. So in this case, we can also change the temperature of this instrument, so we can almost get the real condition of the flue gas. In this case, we can evaluate the membranes for their diffusion coefficient, solubility coefficient, and also for their permeability, and also the auto facilitate effect. Then I'm going to report to you about some of the second part is about O2N2 separation. We are very interested in the O2N2 separation because the O2N2 separation takes up about more than half of the gas separation industry. However, as we know, all the membrane separations rely on the membranes. We can see the power of the membranes. This is the first generation of the O2N2 separation membranes. It was reported by Dow Company in 1984. It was based on the polysulfone with the permeability of oxygen about 1.4 to 1.5 barrel, and the O2N2 selectivity 5.6. But this kind of membrane only it can only have some ability to separate the O2N2 and enrich the nitrogen to about 95%. So it's not economic, it's not competitive. And then in 1990s, most of companies report about the second generation O2N2 separation membranes, like the NEKR product, Involic, UB, and German. And the characteristic of this membrane, the representative of this membranes is that the tetrabromo polycarbonate. The permeability of oxygen is about 1.4 barrel. It's almost the same as the first generation, but the selectivity increased from the 5.6 to about 7.6. But even this very slightly increase about selectivity, what happens is that it has very competitive in generation of 99% of nitrogen. In this case, at that time in the 1990s, almost 10,000 of this small unit of the nitrogen in on-site nitrogen generation setup is working worldwide. If we further improve the O2N2 separation performance of the membranes, so definitely it will push the membrane field a lot, and then we can largely increase the ability of the surviving range of the membrane. But the challenges is how to get high permeability and high O2N2 selectivity and stable membranes. So let's go back to the principle of the separation membranes. If this is the typical module of the membranes, So this is the phase side, and this is return side and permit side. Let's go to the one single hollow fiber that the gas dissolve at upstream and diffuse in the membrane at the downstream of the desorption. In general, we can say this kind of non-porous membranes, the principle is the solution diffusion. There are two parameters. Is the first the permeability for the dense membrane. The higher the permeability, you will save the membrane area, and also another is the selectivity. The higher the selectivity, you will get more pure stuff. So you can also save the pump energy. The Robinson summarized the millions, I think thousands of membranes, and he get to the empirical trade-off curves that called Robinson bond, in which that the permeability and selectivity have some trade-offs, like the higher the permeability and the lower the selectivity, because the power n is minus. So based on the Freeman's theory, Freeman also theoretically analyzed it. So what's the effect of the n? The power n related to the dynamic diameters difference of these two molecules, and also the parameter k related to the chain rigidity, and also the pores, and also the free volume of the polymers. So what we can do, we cannot change the diffusion coefficient. We cannot change the n because the gas molecule, the size is fixed. We can only do something to increase, to adjusting the free volume and also the rigidity of the polymers. In 2004, well, the English guy, two English guys that I called Neil McCann and Peter Barr, they report a special kind of polymer of intrinsic microporosity. This kind of polymer is really special polymers. It was composed of some side contortions and also some shear persistent part. Sometimes it's a net polymer, sometimes it's a semi-net polymers. This kind of polymer, because of this side of contortion, when it's folded, it cannot packing efficient and create some pores. Like we call this different pores with different diameters. That it was reflected by the BET surface, by the BET derived pore size distribution, is that it contains some ultra micropore and nanopores. This kind of polymer is very strange that it has no glass transition temperature. Although recently, some people report that they use flash DSC, they can get this glass transition temperature about 440. That is very, very close to the decomposition temperature of this membrane because they decompose at 450. And this kind of polymers, they have very high bead surface area, around 800 square meters per gram. The most important thing is that we need to emphasize that this kind of polymers, they are solution processable. Now we can process these membranes like conventional polymers that use the solution method, and also it demonstrates very high permeability and modest selectivity. But the selectivity we can, and in this case, the gas transports through these membranes, the mechanism is changed. In traditional polymers, it was solution diffusion mode, and in molecular sieve membranes like zeolite, the gas transports through the zeolites is by the molecular sieving. If the gas molecule is bigger than the pores of the zeolite, it will reject it. It was smaller, then it will transport. But in this PIMS, the PIMS are different because it contains both polymers. They have solution diffusion mode, but it also have pores. These pores, but they are irregular pores, so they can transport the gases, but they cannot efficiently separate them. So in this case, as a result, this kind of PIMS, they get very high permeability but modest selectivity. So how to further improve the selectivity of this kind of membranes is the target we want to get, and we also want to keep their high permeability. So we can create some polymer molecular sieves. We use polymer system, and also we create the molecular sieves inside these polymers. Then we can get both high permeability and selectivity polymers. In my group and during my research, several years of research on this field, I think that we have many methods to to engineering the pores at sub-nanometer scale. Then in this case, we know this pore size distribution. We can change or decrease the nanometer pores and keep most of the ultra-micro pore. In this case, because these ultra-micro pores are in the range of dynamic diameters of the gas molecules. In this case, we can both get high permeability and selectivity membranes. So today I will review some of the methods that we creating polymer molecular cells by sub-nanometer engineering the pores. First, we change the site of contortions, and also we introduce the inter and inter-chain interaction. We also partially filling the pores by physical method. We also use the low temperature method to shrink the micropore. And first, we can change the site of contortion. I think in 2007, I created two polymers. This one, 2-pin polyimide. This pin polyimide is short with short repeat unit. This one with the long repeat unit. And in this case, we can analyze whether the chain folding had the effect on this and the transport properties. In this result, the result turned out that it follows our designs, and this is the extended one. The d-spacing is larger than the non-extended one, and we found that this is their separation performance for O2N2. The chain was longer. This polymer with